Let's start with looking at operational amplifiers, or op-amps. An operational amplifier, or op-amp, is a high-gain linear amplifier. Op-amps are usually packaged in IC form with 1 or 2 op-amps per IC and are relatively inexpensive. The op-amp approaches the ideal amplifier of the analog designer's dreams because it has such ideal characteristics. Firstly, it has a very high open-loop gain in the 100,000 range, but it's unpredictable. It also has very high input resistance in the range of over 1 megaohm, and it has low output resistance in the 50 to 75 ohm range. These characteristics make designing with op-amps relatively easy. As we will see, the high open-loop gain makes it possible to create an amplifier with a very predictable, stable gain of anywhere from 1 to 1,000 or more. The significance of the very high input resistance Rin is that the op-amp draws very little input current. This means it will not load down whatever circuit or sensor is driving it. The op-amp's low output resistance, Rout, means it can drive a load without being loaded down itself. However, an op-amp is a signal amplifier, not a power amplifier. It is not designed to output large currents, and so it is not usually used to drive loads such as loudspeakers or motors directly. This slide shows the symbol for a typical op-amp. It has 2 inputs, V1 and V2, and 1 output, called Vout. Also shown are 2 power supply inputs, which are typically plus 12 volts and minus 12 volts. The output voltage can swing to within about 80% of the supply voltages. Notice there is no ground connection at all. Most op-amps are actually differential amplifiers, which means they amplify the difference between V1 and V2. This is shown in equation 3.1, which is the equation given in the book. The output voltage is the open loop gain A multiplied by the difference between the input voltages, V2 minus V1. The open loop gain A is the raw unmodified gain of the op-amp. It is high, typically 100,000 or more. V2 is called the non-inverting input. You see the plus sign next to it. As the name implies, the output is in phase with the non-inverting input. When the non-inverting input goes positive, Vout goes positive. When the non-inverting input goes negative, Vout goes negative. The non-inverting input is identified by the plus sign. The other input, V1, to the op-amp is called the inverting input. The output will be out of phase with the signal at the inverting input. When the inverting input goes more positive, the output will go more negative, and vice versa. The inverting input is defined by the negative sign, the minus sign in the symbol. Even though the op-amp has 2 separate inputs, there is just one input voltage, which is the difference between V1 and V2. These figures show an op-amp with an open-loop gain of 100,000. Find the output for the following conditions. A. V1 and V2 are both 4 microvolts. B. V1 is 2 microvolts and V2 is 4 microvolts. And C. V1 is 6 microvolts and V2 is 3 microvolts. Note the purpose of this example is only to show you how the open-loop op-amps behave. It would be very difficult to duplicate this in the lab because of the challenges of creating small, steady input voltages. It is not common for op-amps to be used in the open-loop mode, for reasons that will become clear. So looking at case A, where V1 and V2 are both 4 microvolts. The output is 100,000 multiplied by 0, being 0 volts. This shows that the output of the op-amp is 0 if the inputs are the same voltage, regardless of their actual value. For category B, where the non-inverting input V2 is 4 microvolts and V1 is 2 microvolts. The difference between V2 and V1 is 2 microvolts. This multiplied by the gain of 100,000 leaves an output voltage of 0.2 volts. This result shows that the output is positive if the V2 minus V1 quantity has a net positive value.
The difference between V2 and V1 is negative 3 microvolts. This multiplied by the gain of 100,000 leaves an input voltage of minus 0.3 volts. This result is negative because V2 minus V1 has a net negative value.
Consider the 3 op-amps with similar magnitudes of voltage, but with different signs. In figure A, both inputs are positive, yet the output is negative. Why? The negative input, has a larger magnitude, so the quantity V2 minus V1 is negative. 2 microvolts minus 3 microvolts equals minus 1 microvolt. From the op-amp equation, V out equals A times V2 minus V1, you can see that if V2 minus V1 is negative, V out will be negative. Now consider the circuit in figure B. The inputs are both negative, yet the output is positive. To understand this, again, examine that V2 minus V1 and pay attention to the signs. In this case, minus 2 microvolts minus 3 microvolts equals plus 1 microvolts, which is positive. The circuit in figure C is more straightforward. In this case, V2 minus V1 is negative 5 microvolts, which is clearly negative. Another way to determine the output polarity is to use the following rule. The output will assume the polarity that matches the symbol of the most positive input. In the case of figure A, the negative input has the largest positive value, so the output is negative. All the amplifier circuits discussed so far are called open loop because they operate at open loop gain. As we will see, this is not the typical application of an op-amp. We are doing it here because it simplifies the discussion on how the differential inputs work. Now consider the case where only a single input is required. There are 2 possibilities. The output will be either in phase or out of phase with the input. To make a non-inverting amplifier where the output is in phase with the input, the negative input is grounded and the input signal is connected to the non-inverting plus, as shown in figure A. If we want an inverting amplifier where the output is out of phase with the input, we connect the signal into the inverting input, the negative, and ground the plus side, as shown in figure B. The output will assume the polarity that matches the symbol of the most positive input. All amplifier circuits discussed so far are called open loop because they operate at open loop gain. As we will see, this is not the typical application of an op-amp. We are doing it here because it simplifies the discussion of how the differential inputs work. Most op-amp circuits incorporate negative feedback. This means that a portion of the output signal is fed back and subtracted from the input. Negative feedback results in a very stable and predictable operation at the expense of lowered gain. which we can easily afford because the open loop gain is so high to begin with. Analyzing op-amp circuits is actually easier than analyzing traditional discrete transistor amplifiers because the op-amp's impressive parameters allow us to make 3 circuit simplifying assumptions, which we will look at over the next few slides. Assumption number 1, V1 equals V2. How can we possibly assume that the inputs are always the same? Could we not force V1 and V2 to be anything we like? Yes, but the argument goes like this. The output voltage is equal to A times V2 minus V1, where A, being the open loop gain, is a very high number. Thus, even a small difference between V1 and V2 will cause a very large output. However, the output has a practical upper limit established by the power supply. Therefore, to keep the output from exceeding its limits, the difference between V1 and V2 must be very small. This is illustrated in the figure. The power supply is plus 15 volts and minus 15 volts, which limits the output voltage swing to about plus 12 volts and minus 12 volts, that being 80% of the supply. If the open loop gain is 100,000, then the difference between V2 and V1 that would cause an output of 12 volts is computed using the open loop gain equation of V out equals A times V2 minus V1. Rearranging gives us V2 minus V1 equals V out over A, being 0,00012 volts. So we see that to keep the amplifier operating linearly with the output within its bounds, the difference between V2 and V1 must be less than 0,00012 volts, which is a very small voltage. Hence, we say that V1 is virtually the same as V2. The second assumption, the input current is 0. The input resistance of an op-amp is very high. We said before, typically 1 megaohm or more. It is so high that we can model the inputs as being open circuits, as shown. Of course, no current can flow into an open circuit. You could show a 1 megaohm resistor between V1 and V2, but it is simpler to show an open circuit as shown, as current is so low between V1 and V2. The third assumption, the output resistance is 0. A low output resistance means that the output voltage will not be pulled down even if the load draws a lot of current. This is the weakest of the 3 assumptions because the output resistance is typically between 50 and 75 ohms. However, it can be much lower with negative feedback. This assumption only holds if the load being driven is considerably higher than the output resistance of the op-amp, which is the case in most applications with circuit resistance in the 10 to 500 kilo ohm range. Many different types of op-amps are available, with names such as general purpose, wide bandwidth, low noise, and high frequency, to name a few. For most control applications, the general purpose type are adequate. Op-amps come in at least 5 types of packages. 8-pin DIL, which stands for dual inline package. Quad CMOS operational amplifiers offer 4 op-amps in a single package. Metal can, 8-lead TO58 package. High performance audio power amplifier in a single integrated circuit capable of delivering 56 watts. And a 5-pin pentawatt package. This is a high performance audio amplifier designed for car radios. Notice the high power op-amps, numbers 4 and 5, have metal tags with holes. These op-amps are bolted to metal heat sinks to dissipate heat away from the op-amps. Besides the inverting and non-inverting input and output pins, most op-amps have two more pins called offset null. These can be used to adjust the output voltage up or down slightly for the purposes of eliminating the DC offset voltage, a small DC voltage that may occur at the output even when the inputs are exactly equal.